Section 2.5 is limits at infinity, which sounds really similar to what we did in Section 2.4, but it's actually very different. In Section 2.5, we're going to be looking at problems that ask us to solve things like the limit as x approaches infinity for some function. So we haven't seen anything like this. So as x approaches infinity, or as x approaches negative infinity. And what this is called is the end behavior of a graph. Because x approaches positive and negative infinity at the far right and left ends of a graph. So if we had the graph of f of x, and this is just an example of a polynomial. X goes to negative infinity in this direction, and x goes to positive infinity in this direction. And remember, the answer to a limit is what the y value appears to be doing. So what we're asking when we ask the limit as x approaches either positive infinity or negative infinity is, what is the graph doing all the way on the right-hand side or all the way on the left-hand side? In this particular graph, and what most polynomials do, is the y value also goes off to positive or negative infinity. And that's something you might remember from algebra class in something called, the leading term test. If you took pre-calculus algebra with us, Math 171, we learned something called the leading term test that helps us decide the end behavior of the graph of a polynomial. And that's the same as figuring out the limits as x approaches positive and negative infinity. So there's lots of ways to do this, and obviously one of the methods is graphically. But if that is not going off to positive or negative infinity, if it's flattening out at one particular value, like we saw in other sections, it might be hard to pinpoint that exact value. So graphically might not be the best way if we're looking for an exact value. Analytically is the only way that we can truly find an exact value. But graphically and numerically are still perfectly valid. As long as you show what you're doing and you show that you know what you're doing, you can still do them as well, and certainly use them to help confirm your answer. But if you need to find an exact value, analytically would be the way to do it. So you could always do this graphically. You can always take a look at a graph and see what it's doing far off on the right and far off on the left. And those would be our limits as x approaches positive or negative infinity. Now, you might not be given the graph, you might be given the function, and you always have the option to look at the graph. So you could type it into y equals on your calculator and take a look at the graph, or you can type it into Desmos on the internet, which I'm going to do for this example here. We are going to decide, we're going to try to decide the limit as x approaches infinity for, let's say, 3x squared minus 5x over x squared plus 2. And we're also going to do the other side, the limit as x approaches negative infinity for 3x squared minus 5x over x squared plus 2. So for right now, we're just going to do this graphically. So I want to type this function into some sort of grapher. I don't have a way to show you a graphing calculator on my screen, so what I'm going to do is I'm going to type this function into Desmos, which is an online graphing calculator. So we've got 3x squared plus 5x divided by x squared. Let me go back and see. Oh, that was a minus 5x, and then x squared plus 2. I'm sorry, I got a stuffy nose. So that is an interesting graph. 3x squared minus 5x divided by x squared plus 2. I want to know what this graph is doing far off to the right and far off to the left. Well, right now, my graph is only showing negative 10 to positive 10. But we're talking about finding the limit as x approaches negative infinity and positive infinity. So just looking at negative 10 and positive 10 might not give us a very accurate answer. What we should do is probably zoom out a little bit. And see if we can see what's happening. It does appear as though the graph is flattening out at one particular value. And I zoomed out enough now that each of these lines is representing just one unit, because that boulder line right there, it says is 5. And it looks like on the right, it's getting really, 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 really close to 3 from below. And if you want to, we can just keep going over farther and farther, 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 farther. It just gets closer and closer and closer to 3 until it looks like it's right on top. And you can just go farther and farther, farther. This is one thing I love about Desmos, is that it's so much more user-friendly than the graphing calculator. To do this on the graphing calculator, you would have to go into Window and change all your window settings. The calculator is so much more difficult to do things like this. So it looks like as x goes to positive infinity, this graph is flattening out at 3. So that's our answer to the limit as x approaches positive infinity. The y value is approaching 3. Now let's go back and look and see what's happening on the left-hand side of the graph as x approaches negative infinity. So follow it over. Just looking at the standard viewing window, which goes to negative 10, is not enough when we're talking about negative infinity. We really need to go farther than that. And again, it's flattening out at 3. This time it's coming from above, but it's flattening out at 3. And if you go far enough, it pretty much looks like it's just falling on top of 3 and staying there. It really isn't ever touching 3, but it just keeps getting closer and closer and closer and closer and closer. So the end behavior on the left is also 3. And it is common to get the same number for both answers. And what that actually means is that y equals 3 is a horizontal asymptote. Of 3x squared minus 5x over x squared plus 2. Anytime the limit as x approaches infinity for f of x, excuse me, or the limit as x approaches negative infinity, let me go back a little. Sorry, it's kind of sloppy. Whenever the limit as x approaches positive infinity for f of x is equal to some number, or the limit as x approaches negative infinity of f of x is equal to some number, we would say that that number is a horizontal asymptote. And horizontal asymptotes, they're horizontal lines. So we have to write them as equations of lines, which would be y equals L, that number L. And since it's a horizontal line, it's going to be a y equals. So we would say that y equals L is a horizontal asymptote of f of x. So the L has to be a finite number. If you get positive or negative infinity for these answers, then we wouldn't say that we've got a horizontal asymptote at infinity. That doesn't make any sense. A horizontal asymptote is a specific number value that our function approaches far off on the left or right hand side of the graph. And by finite number, we just mean it can't be infinity. If we get infinity, we would say that there's no horizontal asymptote. Okay, so we always have the option to look at this graphically. If for some reason this answer was a really weird fraction or decimal, we might not be able to pinpoint that exact value from the graph. We might be able to get pretty close to it, but we might not necessarily be able to get the exact answer by doing this graphically. But graphically is an option. You can always look at the graph and look off far to the right and the left and see what's happening as x approaches positive and negative infinity. Another option, just like before, is to do this numerically. And numerically is when we set up our charts. So technically, these limits at infinity are one-sided limits. You can only approach in positive infinity from one direction. You can't approach positive infinity from bigger numbers, because technically infinity means get bigger forever. So there is nothing bigger than it. So the limit as x approaches infinity, you can only approach it from below. And the limit as x approaches negative infinity, you can only approach it from above. We don't write the little plus and minus next to it. It's just understood that these are one-sided limits, just because of the nature of the x values that we're trying to approach. So if you do this numerically, you're not having to approach from both sides and make sure that they match up. You only need to approach from one side. And we need to get really large by powers of 10 if we're going off to positive or negative infinity. So if we want to find the limit as x approaches infinity, let's say for 2x over x squared minus 9x, and we'll do this on the left and the right. So limit as x approaches positive infinity and negative infinity. When we do the chart, we want to get closer to infinity by powers of 10. So we'll start with 10 to the first, which is 10, and then we'll do 10 to the second, which is 100, and 10 to the third, which is 1,000. And if you want, you can do another one and do 10,000, but we're trying to go to positive infinity. And then to go to negative infinity, we do the same thing, but negative. So we do negative 10, negative 100, negative 1,000. So we also have the option to do this numerically. And remember, we said the fastest way to do these is to type your function into y equals and have your table in ask mode. And then you can just type in the values that you want. So under my y equals, I'm going to type in 2x divided by x squared minus 9x. And be really careful, if you're not too familiar with your calculator, you need to make sure, and depending on how old your calculator is, you need to make sure that you type that denominator with parentheses around it. Otherwise, your calculator is not going to recognize that there is subtraction in the denominator. It's going to try to follow order of operations and do the division before the subtraction. And it will actually do 2x divided by x squared, and then it will subtract 9x off of the result. So make sure that you have parentheses around your x squared minus 9x so your calculator knows that whole thing is in the denominator. So once I have that in my y equals, I can go to my table, and my table's in ask mode, so I can tell it, all right, give me the y values that go along with 10, and I got 2, 100, and I got 0.022, and then 1,000, which is 0.002. What does it look like these guys are going to? Well, my numbers in the top are going to infinity. We want to know what the numbers in the y row are going to. Graphically and numerically, if this is going to be anything odd, like a decimal or a fraction or a radical, we're not going to be able to find a nice exact value for it. So we're just going to go for the obvious answer. It looks like they're going to 0. If it's anything else, we're not going to be able to pinpoint the exact answer with this method. I will show you in just a minute how to do this analytically, which will always give us an exact answer. So we're also going to do the same thing for the limit as x approaches negative infinity. We just plug the negative counterparts in. So what's happening at negative 10? I got negative 0.105. And then negative 100, I got negative 0.018. And then negative 1,000, I got negative 0.002. And again, it looks like these guys are getting smaller and smaller and smaller and eventually going to 0. So numerically is also an option. We can always make a chart, and with the limits at infinity, we're only approaching from one side. So we can either get bigger and go to positive infinity, we can get smaller and go to negative infinity. And it's still by powers of 10. But this time it's positive powers of 10 because we're trying to get large really, really, really fast. Now, since neither of these methods can always guarantee us an exact answer, our preferred method is going to be analytically. And since technically these are the same as horizontal asymptotes, you may remember from algebra class a shortcut for some of these problems on how you can look at your numerator and denominator and figure out what the horizontal asymptote is going to be. And if we know what the horizontal asymptote is going to be, we know what the limit's going to be. So we can remember from pre-calculus algebra now this works for rational functions. And a rational function is when we have a polynomial in the numerator and a polynomial in the denominator. We can tell what the horizontal asymptotes are going to be just by looking at the degree, or the technically sometimes it's going to be the entire leading term for our numerator and our denominator. So there's three possibilities. We're going to compare our numerator polynomial and our denominator polynomial. If the degree of the denominator is greater than the degree of the numerator. Now, the degree is the biggest exponent in the whole thing. So if I look at my entire denominator and I find the biggest exponent, that's the degree. And then I look at my entire numerator and I find that the biggest exponent, that's its degree. And I want to compare them. Now, if the degree in the denominator is bigger, then your limits are going to be 0 from both directions. Doesn't matter whether you're approaching positive infinity or negative infinity, both of those limits are going to be 0. And I wrote this in limit notation, but what we said in pre-calculus class is that what this means is we're going to have a horizontal asymptote of y equals 0. Well, as long as we get a finite number, that limit is the same as a horizontal asymptote. So another option when we compare those degrees is that they're the same. So if the degree in the denominator is equal to the degree in the numerator, then what we're going to do is we're going to set up a ratio of our leading coefficients. And that's how we get our limit. And we're going to get the same answer on both ends, whether we're doing the limit as x approaches positive infinity or the limit as x approaches negative infinity. So there isn't a really nice way to write this. I'm just going to say it's the ratio of the leading coefficients. And we're going to look at an example of this in just a second. The leading coefficients are the numbers in front of that variable that had the biggest exponent. So if we see that they're equal, if the degrees are equal, then we're just going to use those coefficients from those terms. And then back in algebra class, we described the horizontal asymptote the exact same way, because this ratio of leading coefficients is going to come out to be a finite number. And we said anytime we get a finite number, the limit is the same thing as the horizontal asymptote. Now our last option is if the degree of our denominator is smaller than the degree of the numerator. In that case, our limit is going to be positive or negative infinity. And we need to do a little bit of extra work to figure it out. Oh, I don't want to write equals. So these are infinite limits, like we had in the last section. The answer to these limits are either positive or negative infinity. But to decide whether they are positive or negative, we need to do a little bit of sign analysis. We need to decide what's going to happen if I plug in a really large positive number or a really large negative number with these type of operations that are going on in this function. Will my final result be positive or negative? So if the degree of your denominator is less than the degree of your numerator, that means the numerator is larger. The numerator is going to overpower this function, and our limit is going to be an infinite limit. We're going to have to do some sign analysis to decide between positive or negative infinity. And it might be doing two different things on either side. Whereas in the first and second option, it's doing the same thing on both sides. In option 3, we could get negative infinity on one side and we could get positive infinity on the other side. So both of these end behavior limits would have to be worked out separately if we knew that it was going to be an infinite limit. So I'll make sure we do an example of all of these. So if this is a little bit overwhelming right now, don't worry. So this is technically an algebraic shortcut for doing this. This is not technically the calculus way to do this. I will show you the calculus way in just a couple of minutes. So we want to calculate each limit analytically. So we're going to use this set of 3 rules that we just talked about. We want to know the limit as x approaches negative infinity for 2x plus 5 divided by x squared plus x minus 4. With those 3 rules, we can do this very, very quickly. We don't have to look at the graph. We don't have to make a chart. All we have to do is look at the degree in the numerator and the degree in the denominator and see if they're equal or if the top is bigger or if the bottom is bigger. So the degree in the denominator, we need to look and see where we have the biggest exponent in the bottom, and it's right here. The degree of our denominator is 2. And then we need to know the degree of our numerator. And I don't actually see any exponents in the numerator, but there technically is an exponent on that first term of 1. So we've got to identify the biggest exponent in the numerator and the biggest exponent in the denominator and see which one's bigger. And in this case, the degree of the denominator is bigger. So we said when the degree of the denominator is bigger than the degree of the numerator, the answer for either of these limits is going to be 0. It doesn't matter whether it's asking you as x approaches positive infinity or negative infinity. That's irrelevant. It's going to be the same either way. The answer is going to be 0. This graph flattens out, and it looks like it's approaching the x-axis on the ends. Because remember, this is also a horizontal asymptote. Y equals 0 is the x-axis, so that's why I say that. If you want to confirm, we could always take a look at this graph, 2x plus 5 over x squared plus x minus 4. We were asked what it is doing on the left-hand side. What is it doing as it approaches negative infinity? So far off on the left-hand side, what does it look like the y value is doing? Oops. So Our graph is blue here, and if we go far off to the left, it's pretty much sitting right on top of the x-axis. And the equation of the x-axis is y equals 0. And the farther we go, the closer and closer and closer it gets. And like I just said a minute ago, it doesn't matter whether it asks us for the limit as x approaches negative infinity or positive infinity. Even if they asked us for what's happening at positive infinity, we'd get the same answer. It's doing the same thing on the other side. Now, some really crazy stuff is happening in the middle, but they're not asking us about that. They're just asking us about the end behavior. What's happening far off on the left and far off on the right. It's going to 0 because the bottom's bigger. All right, so our second example, we want to know the limit as x approaches positive infinity for negative x cubed plus 9x divided by 2x cubed plus 5x squared. So for these infinite limits, as long as we have a rational function, we've got a shortcut. And the shortcut is to compare the degree of the numerator and the degree of the denominator. And the degree is the largest exponent. So don't worry about these other two pieces. Don't worry about the 9x and the 5x squared. Those terms have smaller exponents, so we don't care about those. We only care about the term that has the biggest exponent. And those degrees are equal, which means the numerator and the denominator, they're going to grow or shrink at the same rate. The only thing that's going to make them differ is their coefficients. So we're going to set up a ratio of the leading coefficients. So the answer to this limit is a fraction. We're going to start it off as a fraction. Sometimes it will simplify. My leading coefficient in the numerator is -1. My leading coefficient in the denominator is 2. So you could leave it like that, that's perfectly fine, but we get -1/2. That might be hard to see that exact value on a graph. It's not too bad, but if we were to look at this graph, negative x cubed plus 9x, divided by 2x cubed. And then our other term was plus 5x squared. So that's the graph of this function, and we want to know the limit as x approaches positive infinity. So if you look far off on the right-hand side, this one is not getting close to the x-axis the way that we saw the other ones. There's definitely a gap between them. There's a definite gap. If you want to, we can zoom in enough so that we can see that each line represents a single unit. And then if we scroll over, it looks like it's settling about halfway, halfway below the x-axis, which is a -1/2. So that's helpful. We can kind of confirm that it's a -1/2, but it might be hard to just automatically guess a -1/2. If you zoom in even further, then they say the fourth line is -2, which is going to make each of these individual lines a half. So now that first line represents a -1/2, And if we scroll over, we can see our function settles in on that first line, which is a good confirmation, a good solid confirmation that this limit is a negative half. We just have to zoom in enough to that value we want. Now, if it was like 2/3, I don't know if we could get this guy to go exactly to 2/3. Now there it's doing fifths. There it's doing halves. I think we can change some of the things up here. Yeah, we can indicate a specific step size if we want to up here with this little wrench. So there's lots of different things you can do that's really, really useful with Desmos, but we can confirm here eventually that the limit is a negative 1/2. But it might be hard to pinpoint that exact value using the graph alone, using just the graph, because it's a decimal, especially on your calculator, because your calculator screen with the pixels it has can't show a whole lot of detail, and it's hard to zoom in and know exactly how to zoom in and manipulate the screen on your calculator as much as you need to. So here's an example of when our denominator is larger, it's always 0. When the degrees match, we just use the coefficients. The trickiest part is when the numerator is bigger, because then we've got a little bit more work to do. So we're actually going to look at 2 more. The limit as x approaches infinity for 2x to the 5th minus x cubed minus 1 over x squared plus 5x minus 3. We want to know what's happening on this graph as x approaches infinity. It's a rational function, so we can go to our 3 rules above that say compare your degree of your numerator and your degree of your denominator. The degree in the numerator is bigger, which means this is going to be an infinite limit. My numerator value is going to far outpower my denominator value. It's going to get bigger much faster. Anytime your numerator of a fraction gets bigger much faster, the overall value of the fraction is going to get bigger faster. So I know this answer is going to either go to positive or negative infinity. I just need to decide which one it's going to do. So what we do is we say, well, if I'm going to plug in positive numbers, because it says go to positive infinity, we say, what happens if I do 2 times some positive number to the 5th over some positive number squared? Remember, these other smaller terms don't matter. The only thing that matters are the leading terms. And we just need to decide, we already know it's an infinite limit. We just need to decide whether it's positive infinity or negative infinity. So a positive number to a 5th power is still positive, and then times 2 is still positive. So the overall result in our numerator is going to be positive. And then in the denominator, if you square a positive number, you get positive. And then when you divide a positive number by a positive number, you get positive. So this is positive infinity. So what we just did here is sign analysis. We didn't really plug any numbers in. We just looked at the different operations in our function and looked to see what exactly was going to happen with the sign we were using when we applied those operations to them. What was going to happen in the end. So this one was not too bad because everything was positive, it stayed positive, blah, blah, blah. But let's look at another one. The limit as x approaches negative infinity of negative x to the 4th plus 5x over x cubed plus 2. the limit as x approaches negative infinity for negative x to the fourth plus 5x divided by x cubed plus 2. So we've got a rational function and we want limit at infinity. So we compare the degree in the numerator to the degree in the denominator. We don't need to worry about any smaller terms. Now the degree in the numerator is bigger, so we know it's going to be either positive or negative infinity. So we're going to do some sign analysis to figure out which one. So we want to know what happens. Now on this problem, we are plugging in a negative number because we're interested in what's happening as x approaches negative infinity. So we're going to be plugging in some really big negative number. So if I plug in some really big negative number, we're going to be doing the negative of that negative number to the fourth divided by a negative number cubed. If I raise some negative number to the fourth power, any negative number to an even power is going to change to a positive. This result right here is positive. And then I'm going to have a positive times a negative because of the negative in front, which is a negative. So the final result in the numerator is negative. In the denominator, I've got a negative number cubed, which is going to be negative. And then the last operation I have to do is division. I've got a negative number divided by a negative number, which is always going to end up positive. So this answer is going to be positive infinity. So we're just taking the sign from our infinity and looking to see what those different powers and different coefficients are going to do to it in the long run. So these three rules are more of an algebraic way to do this. There is technically a more calculus way to do this. And this is the last thing in this section. Let me check real quick. I was trying to check the time. Sorry about that. Okay. So, if you didn't want to have to remember any specific rules, or if you didn't want to have to look at any graphs or plug in any numbers, and you just wanted a strictly 100% analytical way to do this that didn't require any old pre-calculus tricks, there is a new calculus way to do these. So I'm going to call this the calculus analytical method. There is one rule that it requires, and that is that we understand that the limit as x approaches infinity for some constant over x to any power is 0, where a is a constant. And this is true actually whether we're doing positive infinity or negative infinity. So instead of having to write this twice, I'm going to say positive or negative infinity. So if you think about what's happening here, x is getting either really, really, really large positive or really, really, really large negative. But the numerator is staying exactly the same. So if we look at an example, let's just say 1 over x. If we want the limit as x approaches infinity for 1 over x, and we look at some of the values of 1 over x, the numerator is staying a 1, but our denominator is getting larger and larger and larger and larger and larger. So 1 over 1 is 1. And I'm just picking some random values that get bigger. 1 over 2 is a half. 1 over 3 is a third. 1 over 4 is a quarter. So I'm picking x values and I'm plugging them into my function here, 1 over x, and looking at the y value that goes with them. If I plug in 10, I get a tenth. If I plug in 100, I get 1/100th. If I plug in 1,000, I get 1/1000th. So as that denominator gets larger and larger and larger, the value of the fraction gets smaller and smaller and smaller and smaller. As long as your numerator is a constant and your denominator is a variable. And your denominator is allowed to have an exponent, and that would just make it get to 0 even faster. And it doesn't matter whether we're going to negative infinity or positive infinity. It would still be the same. So as long as we understand this rule, that anytime we have the limit as x approaches positive or negative infinity of some constant over x, it's going to be 0, we can do this with a purely kind of calculus analytical method. So what we're going to do is we're going to identify the largest degree in the entire function. And then we are going to divide every single term by it. As long as you do it to everything, then mathematically it's legal. We're allowed to do it. And then everything is going to simplify to 0 except for the biggest term. That will leave us with a constant. So this is a purely analytical method. Doesn't require us to memorize rules and compare powers. If we want the limit as x approaches negative infinity for, let's say, 2x to the 5th minus 3x squared over 5x to the 5th plus x cubed. Now, we probably know the answer already because we learned the shortcut method, but I just want to show you an example that we can work without memorizing any shortcut methods. This purely analytical calculus method. So the analytical calculus method says identify the largest degree in the entire function. The biggest power in the entire function is 5. So what we're going to do is we're going to divide every term by x to the 5th. As long as you do it to everything, then you're not breaking any math rules. So I'm going to go in and I'm going to divide everything by x to the 5th. And I'm not going to simplify anything yet. All I'm doing right now is I'm taking all 4 of those terms and dividing them by x to the 5th. Because we decided x to the 5th, that's our variable with the biggest degree. Now we can do a bunch of algebra simplifying. So here they cancel completely. Here they cancel completely. Over here we can do a little bit of simplifying. I can cancel 2 here and 2 here, leaves me with 3. Cancel 3 here, sorry. If I cancel 3 here, it will leave me with 2. So we're going to rewrite what we've got. So that's going to just leave me with 2 minus 3 over x cubed divided by 5 plus 1 over x squared. And this is where that new limit rule comes in handy, because if we have any pieces that have a constant over a variable, they're going to go to 0. So I'm going to scroll back up to that. Any pieces look like this, we just mark them off. They're going to 0. So if any pieces left still have a constant over a variable, they're going to 0. We have 2 like that. 3 over x cubed is going to go to 0. 1 over x squared is going to go to 0. So what are we left with? If those 2 are going to 0, all we're left with is those 2 front numbers, 2/5. Which is the exact same thing we would have gotten with the shortcut, because we would have recognized that they've got equal degrees and we would have used the coefficients. But it doesn't require us to memorize those rules, especially if you don't remember those rules, if you took algebra a really long time ago, or if you just never learned them to begin with. You don't necessarily need to learn them now. You could do this instead. And it would avoid having to memorize all those new rules. You just divide out whatever that biggest power of x is, and then simplify, and you'll get your answer. The one other thing we need to address really quickly before we wrap up this video are our transcendental functions. Transcendental functions are functions that cannot be written as powers of x. So some examples of transcendental functions are our trigonometric functions, exponential functions, our logarithmic functions. Those are all transcendental functions. We don't write them like we write polynomials. They've got their own special rules. So they don't follow any of the rules that we just talked about. So if we were asked to do limits, any type of limit of transcendental functions, we can't really do them analytically. We might be able to do them with direct substitution if they work out nicely. But if they come out as 0 over 0, which is our indeterminate form, or if they ask us for limits at infinity or infinite limits, we're going to have to either look at the graph or we're going to have to make a table to do these for right now. We don't have any special rules really to do trigonometric limits. One very popular graph that we're going to see in a lot of application problems is the e to the x graph. So if we want the limit as x approaches infinity for e to the x, really it's asking us, what does the e to the x graph do on the right hand side? So the easiest way to determine this is to remember what the e to the x graph looks like. The e to the x graph is really flat on the left, but then it shoots off to infinity on the right. So our e to the x graph, as x approaches infinity, so x is approaching infinity over here on the right, the y value is also shooting off to positive infinity. But on the left-hand side, the limit as x approaches negative infinity for e to the x. So this direction is where it's going to negative infinity. On the left-hand side, it's flattening out and getting really, really, really close to the x-axis which has a y value of 0. So whereas our rational functions, if we got a finite answer, we saw that it was almost always doing the exact same thing on both sides. These transcendental functions are very, very, very different. And there's really no special rule for figuring this out. We just need to either set up a table, do it algebraically, numerically, or look at the graph. The limit as x approaches infinity for sine of 2x. So we need to know what the sine of 2x looks like. So the sine graph looks like a wave that starts at the origin. The 2 inside of our angle is going to affect our period. The period is how long it takes to do one full wave of the graph. So the 2 in there is going to make it go quicker. So it's going to do one full wave in a distance of pi. And then it just keeps doing that over and over and over again. And then it does the same thing this direction. So as x approaches positive infinity, we want to know what the y value is approaching. Is the y value approaching a specific number? And in this case, it's not. It just keeps going up and down and up and down and up and down and up and down forever. It's never going to settle in on one specific number. It just keeps oscillating back and forth between y values of positive and negative 1. What we're looking for in a limit is we're looking for our y value to eventually settle into one specific value. And this graph does not do that. So we would say that this limit does not exist. Because this sine graph never settles down. It keeps making that wave over and over and over again. And the same would be true if we did the limit as x approaches negative infinity. So some different things to think about with transcendental functions. They don't follow the same rules. They don't follow these 3 rules we just talked about. And we don't really have special rules for them. You really are just going to have to look at them either graphically or numerically to help you decide. So you really have to have a good understanding of these limits at infinity, that when they ask you the limit as x approaches negative infinity, they're asking you the y value that the graph is settling into on the left-hand side, and the limit as x approaches positive infinity is the y value that the graph is settling into on the right-hand side. Because especially for these transcendental functions, that may be the only way that we're able to do them for right now. Once we learn some more calculus, we might be able to learn some analytical methods for a few of them, but even then, still not all of them. So some other options besides rational functions.